Here is my final counting circuit breadboard prototype. A step-by-step process of this build will be explained in this video, from an analog input to a NAND gate oscillator all the way to a 7-segment display. The tens digit has to be 10 times slower than the first, so the carryout output of the 4510 chip for the ones digit is connected to the clock signal input of the 4510 chip for the tens digit. This build is able to adjust the frequency of the counting by using a potentiometer instead of a fixed resistor in the RC2 section of the NAND gate oscillator, which will be explained later in this video. A counting circuit starts with a button input. There are two options when doing a button input, a high or a low side switch. The first is a high side switch, which when pressed, the output is a high. The second is a low side switch, which when pressed, the output is a low. This circuit uses a low side switch. This next step adds a NAND gate oscillator to the analog button input. This circuit creates a clock signal output when the button is pressed. The clock signal consists of a high and low frequency. The duration of the clock signal can be changed depending on the resistance or the capacitance in the RC1 section of this build. The higher the resistance or the bigger the capacitance, the longer the duration will last. And the frequency of the clock signal can be changed depending on the resistance or capacitance in the RC2 section of this build. The lower the resistance, the faster the frequency, and the higher the resistance, the slower the frequency. The same goes for the capacitor. The lower the capacitance, the faster the frequency, and the higher the capacitance, the slower the frequency. This is the decade counter build, which adds a 4017 chip to the NAND gate oscillator. The clock signal is inputted into the clock input of the 4017 chip. This chip creates the effect of a ring counter, where for each high-low cycle the clock signal inputs, it creates a high for one of the 10 outputs at a time. This process goes all the way around the chip, giving a ring effect. To see the result, you plug in a 10-segment LED bar graph, where each LED is connected to an output. The connection is ordered from smallest to biggest numerically, to left to right. The product will make an LED bar graph appear to count from left to right. The divide by 10 pin completes a full high-low cycle every 10 times the clock signal input creates a full cycle. This can be used to create multiple digits in a counting circuit. This next step converts the ring counting output into a binary counting output from 0 to 9 and repeating. This can be achieved by connecting the 1, 2, 4, and 8 outputs of the 4017 chip to their corresponding 1, 2, 4, and 8 inputs in the 4510 chip. The 4 outputs of this chip are then connected to 4 LEDs ordered smallest number to the biggest from right to left. The product will be a counting circuit in binary, counting numbers from 0 to 9. When the reset pin is plugged in, it allows the counting to reset. Once it hit 9, it can go back down to 0 and repeat. The up-down feature of this pin allows the binary count to either go up or down. If the input is high, the circuit will count up. If the input is low, the circuit will count down. The next step of this build converts the binary counting into a decimal output that could be shown in the decimal number system with a 7-segment display. This can be achieved by connecting the 4 binary counting outputs from the 4510 chip into their 4 corresponding binary inputs in the 4511 chip. To see the result, you connect the 4 outputs of the 4511 chip into their corresponding inputs in the 7-segment display. In this image, the 4 switches represent the 4 binary outputs of the binary counting up and down counting chip. The 4511 chip then connects those outputs into their corresponding binary inputs. Then, the 7 outputs of this chip are connecting to their corresponding inputs in the 7-segment display. Each time a binary number is produced, the 4511 chip converts it into a decimal number system counting output. The table on the right is a high-low table for each segment in the 7-segment display. This is the final PCB counting circuit display. This build implements all the parts of the breadboard prototype onto a PCB circuit board. This build replaces all the resistors for the 7-segment display with 2 resistor networks. This allows the space for the circuit board to be much tighter and compact.